Okay, in this mechanical vibration lecture series, today's lecture is focusing to discuss one of the vibration control method, use of vibration absorbers. Vibration absorbers also are spring mass damper systems which used to minimize the amplitude of the vibration close to the system natural frequency. That means resonance frequencies. Okay, let's move the theory under this topic. Today we are going to discuss about the use of vibration absorbers. Use of vibration absorbers to minimize the use of vibration absorbers to minimize the amplitude of the vibration. Okay, first we are going to discuss about the undamped vibration absorbers. Okay, undamped vibration absorbers. Okay, undamped vibration absorbers. First we are going to discuss vibration absorbers. It also a spring mass system. Then what happen when using the vibration absorbers? Energy transfer into the system is taken by this absorber. Then absorber is vibrating without vibrating the system. Let me explain this one. Let's take this kind of system. Let's take the system mass as m1. The excitation force F cos omega t is applied on this m mass. Then the system stiffness we are going to represent by the two springs which is connected parallelly. So then one spring is, let's take k1 divided by 2, then both the resultant stiffness is equal to k1. Okay, the resultant stiffness of the system is equal to k1. The total mass is m1. Then this is the excitation force acting on the system m1. So then absorber also a spring mass system. Let's take this kind of spring mass system. Let's take this spring stiffness as k2. Then let's take this one as m2. Okay, then this part is called absorber. It also a absorber, also a spring mass system. In the undamped situation, it is not having the dampers. Okay, then what happened in this situation? This excitation force acting on this m1 mass, that means it continuously transferring energy to the system. Okay, continuously transferring energy to the system. Then what happened? This transferring energy is taken by this absorber. Okay, this is how we are designing this absorber, where all the energy transferring through the excitation force should be able to take by this absorber. So then what happened? Absorber vibrate. This absorber vibrate without vibrating the system. Okay, that means the absorber should be able to acquire all the energy transferring by the excitation force. Then what happened? This absorber vibrate without vibrating the m1 mass. That is in that way we have to design the absorber. Designing the absorber means we have to design the k2 and m2. That means the spring stiffness and the mass we have to decide the we should know to design the absorber for a certain system. Okay, let's see how to design a absorber. How to design an absorber means deciding k2 and m2. Okay, in undamped situation. Okay, and here first we are going to discuss about the undamped situation. In undamped situation, when designing an absorber to a system mean we have to decide the k2 and m2. Okay, let's see how to design that one. Okay, actually this one also called vibration neutralizer, and also it also called dynamic vibration absorber, and also called vibration neutralizer. Okay, let's take I am assigning the coordinate frame, let's take to the ground the movement of the m1 mass, let's take it as the x1t. To the ground the movement of the m2 mass, let's take it as x2t. Okay, x2t. So then displacement is x1t, then velocity is equal to x dot 1, the acceleration is s double dot 1. Okay, like that. Then I'm going to apply F is equal ma, Newton's second law. F is equal ma considering the motion of m1 mass. Okay, F is equal ma, Newton's second law, considering the motion of m1 mass. Okay, consider the motion of m1 mass. I am going to apply Newton's second law. F is equal ma. So then what are the forces acting on this m1 mass? What are the forces acting on this m1 mass for a certain time? The excitation force directly apply. If cos omega t force is applied, then let's take the situation where this the movement as x1. So then spring has compressed by x1 distance. From this both the spring, what are the spring stiffness, spring compression x1. So then what is the due to that what is the force acting on it? That is acting upward direction. The compressive force generated by the spring is acting upward direction, so the minus k1 x1. Okay, k1 x1. Okay, that is equal t situation. So at the same time you can see this spring also has a displaced by x2 amount at the t is equal t situation. It has stretched by x2 amount, so that because of this stretch of the k2 spring, what happened? Downward force acting on the m1 spring. Okay, but we have to think relative movement of the m2 mass. This one also moving x1 distance, this one also moving x1 distance, at the same time this one moves x2 distance. So what is the total extension of the k2 spring? What is the total extension of the k2 spring? It is equal to, extension is equal to x2 minus x1. x2 minus x1, total extension of the k2 spring, because both the mass are moving, so that we have to take the total resultant movement. So that that is equal to plus, because it is acting downward direction. I am taking the stretch of the spring. That is equal to k2 x2 minus x1. Then these are all the forces acting on this m1 mass. Okay, these are all the forces acting on this m1 mass. Let's take the F is equal ma, m1, the acceleration into the downward direction, we are applying in downward direction, then x double dot. Okay, this is the differential equation. We can write considering the motion of m1 mass. Okay, then again we can write another equation, differential equation, second order differential equation, considering the motion of m2 mass. Okay, consider the motion of m2 mass. I am going to apply F is equal ma to the downward direction. F is equal ma to the downward direction. So what are the, consider the m2 mass, what are the forces acting on it? Okay, what are the forces acting on it? So then let's take I am applying in downward direction. Earlier we discussed this is the stretch, amount of the stretch, so that in a downward direction, that is minus k2 into x2 minus x1. Okay, because of this spring. Okay, so then that is equal to m2 x double dot. Okay, this is the only force acting on this m2 mass. Okay, this is the only force acting on this m2 mass, stretch of the spring, and also the m2x double dot is the this part. Okay, then we are having the two equations. We are having the two differential equations. Equation 1, equation 2. Okay, equation 1, equation 2. These equations we can when we are going to find the solution for this differential equation, both the differential equation, we are having the complementary function solution and the particular integral solution, as we discussed in the previous lectures. You are familiar with this solving this second order differential equation. When solving this differential equations, we are in the two part called complementary function solution. That complementary function solution we are obtaining by equating right hand side to 0, then right hand side to 0. So then we can rearrange this equation also. So then the particular integral solution. So then in steady state situation, we discussed in the previous lectures also, in steady state situation only the particular integral part is remaining. Okay, that particular integral solution we can write in this kind of format. Okay, in steady state situation, steady state condition only particular integral part is remaining. Actually these things we discussed in discussing the damped vibration systems, so I'm not going to simplify all the things. So then steady state solution for this equation 1. For equation 1 we can write in this kind of format: x1t is equal, x1 is a constant cos omega t. Then from the second equation we can write x2t is equal x2 cos omega t. Okay, in this kind of format we can write steady state solution of the differential equation. Okay, then steady state condition we can write these both the equation as the solution of this differential equation. This is the particular integral part. That means x1t and x2t are the particular integral part solution of these two differential equations. Okay, since these two are particular integral solution of this both the differential equation, these differential equation should be able to satisfy by its solution this particular integral solution. So that I am going to substitute, differentiate and substitute this solution in this differential equation in order to find the x1 constant. Okay, same as here. Then if you can substitute this solution, that means for example, let's take here first solution x1t, the x1 dot t is equal x1 omega sin omega t, x double dot 1t is equal minus x1 omega square cos omega t. Okay, then these solutions at the same time we have to find this one also, x2t dot is equal minus x2 omega sin omega t, x double dot 2t is equal minus x2 omega square cos omega t. Okay, so then By substituting these equations in these both the equations, in these differential equations, we can derive expression for x1 and x2. Okay, by substituting this equation in this equation 1 and equation 2, we can derive expression for x1 and x2. So I'm not going to do that one. You can try it at home. So I am going to write the expression I obtained. Okay, x1 and x2. Okay, the expression for the x1 and x2 we are obtaining for both the by solving this both the equations. For x1 we are getting k2 minus m2 omega square excitation force frequency magnitude divided by k1 plus k2 minus m1 omega square k2 minus m2 omega square minus k2 square. Okay, this is the x1 we are obtaining after simplifying all the equations. So then x2 also we are obtaining this kind of expression k2f divided by k1 plus k2 minus m1 omega square k2 minus m2 omega square minus k2 square. These are the two constants values we are obtaining after simplifying both the equations. Then this is the x1 and x2 we are obtaining by simplifying both the equations. That means for x1 and x2 in steady state vibration, here what is meant by the x1, amplitude of the vibration in steady state situation. That means if you take the m1 mass, let's take, I will explain this one. If you take the m1 mass, m2, this is k1, k2. Okay, then what is meant by the x1 mean? X1 mean in steady state situation, amplitude of the vibration of the m1 mass is called x1. Okay, x1, this amplitude of the vibration, this is called x1, x1t. Okay, so then this one x2 mean amplitude of the vibration of the absorber mass. Okay, in steady state situation, amplitude of the vibration of the x2 mass, here x2t, and this is the amplitude of the vibration of the x2 in steady state condition. Okay, steady state condition. Then here you can see in steady state situation the amplitude of the vibration is given by this equation. Actually we are interested about the vibration of the m1 mass. This is the system. Okay, this is the system. We are interested about the vibration of the m1 mass, not the m2 mass. We have to minimize the amplitude of the vibration of the m1 mass. Okay, system amplitude we have to reduce. So that let's take this system is this absorber is designed to minimize the amplitude of the vibration closer to the resonance frequency. So that means you all know at the resonance frequency this system vibrate with very high amplitude of the very high amplitude. So that these absorbers are designed to minimize the system vibration at resonance frequency of the system. Okay, resonance frequency, because at the resonance frequency system vibrate with increasing amplitude. Then what is the resonance frequency of the system? Resonance frequency of the system, that is equal to omega is closer to omega is equal to k divided by m square root. K divided by m square root. Okay. Okay, sorry. K1 m1. Okay. So then we are interesting about reducing the amplitude of the vibration of the m1 mass. So then this is the amplitude is given by this equation. How to make x1 equal to 0? Okay, you can see the numerator and denominator. So then if we can make this part into 0, we can take x1 to 0. Then how to make this part into 0? Here the multiplication of two terms. So then inside this bracket, if we can make this inside in this bracket into 0, we can make x1 into 0. So then what happen? How to take x1 into 0? If we can design an absorber, k2 minus m2 omega square is equal to 0. So then what happen? x1 goes to 0. x1 is equal to 0. Okay. So what is this condition? That means design absorber natural frequency should equal to the excitation force frequency f cos omega t. This is the excitation force frequency. Design absorber frequency should equal to the system excitation force frequency. In that, if we can design that kind of absorber, what happens? We can take system vibration to 0. So that means if you simplify this one, omega square is equal k2 divided by m2. Okay, k2 divided by m2, the omega is equal k2 divided by m2 square root. Okay. Then what is happening in here? If we design absorber which having the system natural frequency same as the excitation force frequency, what happen? All the energy transferring from the excitation force can absorb by the absorber, because both the frequencies are same. So that this absorber can take all the energy transferring from the excitation force. So that absorber vibrate without vibrating the m1 mass, because all the energy transferring to the absorber, then no energy remaining for the vibration of the m1 mass. That is the theory behind this absorber. So that when designing absorbers for this kind of undamped situation, what is the condition? We have to design absorber system natural frequency should be equal to the excitation force frequency. Okay, this is the design condition for the absorber. That is called system excitation force frequency should equal to the absorber natural frequency k2 divided by m2 square. This is the design criteria when designing an absorber for a certain system. Okay, that is called the tune vibration absorber. Tune vibration absorber means this vibration absorber is tuned to operate at system natural frequency, because we are interesting about the minimization of the system vibration. You all know system vibrate with very high amplitude, closer to the system natural frequency, so that these absorbers are designed to reduce the system vibration at the system natural frequency, so that in design tuned vibration absorbers are designed. The omega square is equal k2 divided by m2 and also k1 divided by m1. This is the condition. Okay. What is mean by this k1 divided by m1 mean? This system natural frequency. Okay. If what happen if excitation force frequency is coincide with the system natural frequency, this system is vibrating with a very high amplitude. The absorber is designed to minimize that amplitude of the vibration, so that this is the condition for the tuned vibration absorber. Tuned vibration absorber natural frequency should equal to the system natural frequency, and also this equal to the excitation force frequency. Okay. Well, let's take the example problem, so then you will get more clear idea about this one. Okay, let's take this example. A tuned vibration absorber is to be designed to eliminate the resonance problem with a machine that can be considered as the mass of 120 kg, mounted on a spring of stiffness 30 kN per meter. The mass of 50 kg is to be used for the vibration absorber. Calculate the necessary absorber spring stiffness. This problem is undamped problem. The system damping properties are not given. That means it's an undamped problem, and also the absorber also undamped absorber. So then let's see how to design this absorber to minimize the amplitude of the vibration. Okay, let me draw the sketch of this diagram. First of all, then the mass given. This is the system. The total mass of this system is 120 kg. The stiffness of this spring, resultant stiffness, is equal to 30 kN per meter. So then we have to design the absorber. That tuned vibration absorber is designed to eliminate the resonance problem. That means the resonance problem. So then that means we have to design the absorber to avoid the. Well, then this vibration absorber has to be designed to eliminate the resonance problem. Eliminate the resonance problem means resonance happen when excitation force frequency is coinciding with the system natural frequency. That means if cos omega t, this is the excitation force frequency. Resonance occur when what happen? This omega is equal to system natural frequency, omega n. So system natural frequency is equal to the k divided by m square root. Okay. At this frequency, to avoid the resonance, we have to design the absorber. So that means absorber should operate on the system natural frequency. So that what is the absorber? Undamped absorber we are going to design. Spring and the mass. Let's take M2. No, sorry, that is given, no? Yeah, 50 kg is given. Sorry, this is 50 kg is given. 50 kg is given. This is not given. Let's take this as K. So only thing we have to design the K. Okay. Only thing we have to design the K. That means this absorber should be able to absorb energy transferring at this frequency. At this frequency mean resonance frequency. So what is the resonance frequency? Let me find this resonance frequency. this resonance frequency K divided by 30. At this resonance frequency, this is the resonance frequency. At this frequency, absorber should be able to absorb energy transferring from the excitation force. So then, in a tuned vibration absorber, the condition, what is the condition? The K1 divided by M, that means the system natural frequency should be equal to K2 divided by M2. That means absorber natural frequency. Because this absorber is designed to operate in resonance frequency condition. Okay, we want to reduce the amplitude of the vibration system at the resonance frequency, so that vibration, that means this machine is, we can assume this machine is operating at the resonance frequency, so we are designing an absorber to minimize the amplitude of the vibration of the system at the resonance frequency. So then K1 divided by M1, okay, K1 divided by M1, take the 30 in kilonewtons, let's take, no problem. Then we are getting the K2 in kilonewtons, the 120, that is equal to K2, the M2. The M2 is given, the 50 kilogram is given. So then K2 is equal 30 into 50 divided by 120. So for the K2 is equal 12.5 kilonewton per meter. Okay, this is the answer. 12.5 kilonewton per meter. If we design this kind of absorber, that means the absorber stiffness is equal to 8.5 kilonewton per meter. So then the 50 kilogram, that data is given. If we design in that way, what happens? The energy transferring from the excitation force taken by the absorber vibrate with high amplitude without vibrating the system. Okay, all the energy is transferred into the absorber, and absorber vibrate. Okay, this is how the absorber operate. Okay, this is all about the absorbers. Let's continue on next day class.